extremely happy to have Péter Biró from Corvinus University of Budapest and Institute of Economics. So Péter Biró is famous in his work on matching markets and market design, but more he is famous in the practitioner work, which is much more important, I think, at least for me, it's personal opinion. So we're very happy to have Péter. And Péter, you have 1 hour, right? Correct. And yeah, the floor is yours.
Thank you very much for the invitation to Rabat. I'm really impressed by this nice campus and all this nice research group here. So my talk is going to be about kidney exchange problems and some optimization and game theoretical aspects. So hopefully this will be also useful and interesting for the students who are actually attending the game theory course that I'm teaching this week, because today we will use some TU and also some NTU games to describe some problems for kidney exchange. It's quite interesting. In a kidney exchange, obviously there is no money involved, so you cannot buy and sell kidneys. But still, you will see that TU games can be used to get some reference points for a fair solution. So just today in the game theory class, we studied Shapley value, Banzhaf index, and actually we use these values as a reference point in some applications. All right, so first of all, so this is the overview. So first, the first like 20 minutes, I will speak about kidney exchange problem, what is the practice in Europe. In the last 10 years, we have been working on various projects in Europe, cost action, and lately a new project, EU for Health, funded. So it's a big European project with a consortium having all the essential partners in Europe, and we see how this is working in practice, and also we understand the challenges and we understand the what are the main goals. However, even the decision makers are sometimes unsure, what to do, how to define policies. Optimization policy is just a part of the whole process when you design a mechanism like a kidney exchange program. One consideration, for instance, whether or not the countries should join forces and collaborate with each other, maybe at the European level, to have even more transplantations. And what we are doing, actually, we are trying to advise the decision makers. We are doing studies, simulations, and based on the findings, they can decide, how to shape the European practice. So this is a process in two directions. We learn what are the main questions in Europe in practice, and then based on our simulation findings, like agent-based simulations, what we are doing, they can also shape their policies. And in the second part, I will talk about individual fairness based on the quality of transplants, which is an individual decision for the patient pairs and the clinicians advising them. And surprisingly, here, core solutions, stable solutions will come up, and the famous TTC algorithm that I don't teach in this class this week, but I think it's good that the students can hear about this mechanism, because this is really a standard model and solution. And I will show that there is a new property that we proved recently, respecting improvement property, how this has an effect in the applications. And finally, I will speak about international kidney exchange. How can we motivate the countries to join forces, and in particular how we can balance the benefits of international collaborations. All right, so we had a lot of papers recently on this topic. The first 2 papers are about European practices, so this is going to be covered in my first 20 minutes. Then the second are about stable exchanges, so solutions in the core, and the respecting improvement property. And finally, international kidney exchange programs. So originally, we published these papers in a AI conference series, AMAS, but later all of them actually got also published in journals. So we have EJOR and math programming papers and an AI journal paper from those 3 publications. Okay, so what is a kidney exchange? So if you have a kidney problem, you can wait for a deceased kidney, but this can take many, many years. So living donation became quite a standard practice. But if you have a willing donor, maybe your spouse, then it's possible that this willing donor is not compatible with you, either by blood type incompatibility or so-called HLA incompatibility. In fact, wife who is sick and needs a kidney, unfortunately, if they have a common child with the husband, it's actually quite possible that the wife has some antibodies already developed against the husband because of the common child. So in these situations, actually, what can they do? They can join a kidney exchange program, and they can exchange actually the donors in such a way that in the end everybody will receive a fully compatible kidney. So the first example is a so-called pairwise exchange with 2 patient donor pairs, and then you can see a three-way exchange. And usually these exchanges are bounded because they have to be conducted simultaneously, so at the same time. And with a three-way exchange, you already need 6 operations at the same time. So this is challenging. So the only case when you can do this in a more relaxed way is when you have an altruistic donor. So in many countries, they allow that a donor can give a kidney just by altruistic reason, as a good Samaritan, and then you can start a chain, and this chain can be actually pretty long. So already when Errol presented his Nobel lecture back in 2012, he showed in his Nobel lecture long chain in the US with, I think, 30 or 60 patient pairs. So in this case, you don't necessarily have to do these transplants at the same time. But not all the countries are allowing actually altruistic donations. So for instance, in Hungary, this is forbidden. Yes. Yeah, I will come back to that. Yeah. So this is an old picture taken 2007 when I was a postdoc researcher in Glasgow in the computer science department with David Manlove and Rob Irving. And with David, we developed an algorithm for the UK kidney exchange program that actually we used later on for computing the optimal solutions. So this was in the newspapers back in 2007. This was actually the second pairwise exchange conducted in the UK. So this lady wanted to donate to her father, but she was incompatible. So instead, she donated to that lady, and in return, her husband donated back to the father of the original donor. And so in the UK, so this is a paper from 2009, and we describe what happened in the early days, in the first 2 years, 2008, 2009. And you can see that match runs are conducted in every 3 months in the UK, which is very typical in Europe. And there are hundreds of patient pairs. So nowadays it's even bigger, like 300-400 of patient pairs are participating in a match run. So in October 2008, there were 123 patient pairs with more than 700 possible transplants, which are compatible transplants. So the best solution with 2 cycles was of size 12, so 6 2 cycles. With 3 cycles, we could have achieved 25 transplants. Actually, it's also possible to compute the maximum with unbounded cycles, which is not realistic, but still interesting. And in the end, what the policymakers decided as a solution to choose is when the maximum number of 2 cycles was 6, and there were additional 3 cycles, so 3 cycles, and giving 21 transplants selected. So these were the early days, and then we had a cost action. So this was a big project with yeah. Mm-hmm. Yes. Yeah. No. Usually they have a very clear policy, an optimization policy. Yes. This is their decision, so their policy. Yeah. Yes. So I will come back. I will show you what are the optimization policies in Europe, because we surveyed that in this project. So we did 2 surveys. I was responsible for that. I was leading that working group. The first survey, was about all the aspects of the kidney exchange programs in Europe, and then we could see, which countries have kidney exchange program, which countries doesn't, and whether these are large and well-operating programs or relatively small and not so well operating. And there are also some international collaborations I will talk about later. So essentially, so this is a picture from that survey back in 2016. So already the UK was the largest program. So total number of transplants conducted until 2016 was around 700. Today it's more than 2,000. They have already performed more than 2,000 transplants in the UK. By the way, next week there will be a webinar about the UK kidney exchange program. So if you are interested, you are all welcome to attend, because this is free for everyone. In fact, we could also convince the German decision makers to attend this seminar. They are just about to pass a new legislation allowing the German kidney exchange program, because this is currently kind of forbidden in Germany. Yeah, that was also the case in Germany. Now they are passing a new legislation. Actually, in Hungary, the kidney exchange program started 2024 summer, and this January we had the first successful pairwise exchange in Hungary. Yeah. So yeah, it's a good question. So in Europe, first of all, there are a lot of collaboration about deceased organ donation. So there is Eurotransplant covering 8 countries, including Hungary and Germany and Austria and others. There is also Scandia Transplant for Scandinavian countries, operating already like for 50 years. And actually, Tommy Andersson and his colleagues, they could manage to convince Scandia Transplant to also organize the kidney exchange program. So for Scandinavian countries, the kidney exchange program is taken care by Scandia Transplant. Eurotransplant was not willing to take this for Eurotransplant countries. For Southern Europe, there is a collaboration between Italy, Spain, and Portugal. They actually joined their kidney exchange programs, more or less. They also have some kind of collaboration with France for this is organ allocation. So probably that would be the most realistic, I think, for Morocco. If Morocco wanted to start either their own kidney exchange program, a national program, or to join already some collaboration. I think, you know, Spain is, I mean, so close, so it's because it matters actually, the distances can matter because these transplants should be done simultaneously. So the, you know, when you ship the organs, they should arrive in a few hours. Okay, so the UK program was already the largest back in 2016. I don't have the last figures. Actually, I have on my computer, but not in the slides. Sorry for that. But as I said, UK is very much the best program regarding the number of transplants. So they already performed more than 2,000, which is much more than all the other countries combined. So that's why actually now in the new project, everybody wants to kind of copy what the UK is doing because they seem to be very efficient. And but Spain is also pretty big, and the Dutch program was actually the first in Europe, started in 2004. So they also have a huge experience with kidney exchange. Yeah, yeah.
So in terms of percentage, still, again, it's very important. It's funded life saving.
Yeah.
What do you think the barrier to expand it? Because still on the level of percentage, it's probably relatively small, below 10%, I believe, right?
Yeah. So we have a new paper actually published in Health Policy with David Manlove and German colleagues. So Axel Ockenfels, probably you know him. He's really an economist who is very active in advising policymakers. So in all sort of market design problems like auctions and also kidney exchange. And so in that paper now we have also some numbers, you know, number of living transplants. And, you know, there are some medical details which are quite important. So actually, if you are HLA compatible, but ABO incompatible, so blood type incompatible, so you have a blood type A and your wife has blood type B, the donation is still possible, just you have to go through a so-called desensitization treatment. This costs like 100,000 euro. You have an extra risk of 2% of kidney failure, so the quality is worse. But in many countries, they still do this direct transplant, including France, Italy, and this is the standard treatment. In other countries, like in the UK, they ask these ABO incompatible pairs to join the kidney exchange program, wait for 1 or 2 match runs at least, because they can get a better quality kidney, a fully compatible kidney, and by the way, they can also save a lot of money because they don't need to do the desensitization treatment. So if you see the numbers in the table in our new paper, it's very clear. Those countries who have a good performing kidney exchange program like the UK, the percentage of ABO incompatible living transplant is around 5–8%. In other countries like France, Italy, and Germany, the percentage of ABO incompatible transplants is around 20%, 20–25%. So much more, a lot of waste of money and also worse quality kidneys. So what we argued in this paper about the German policy is actually to convince them not just to encourage the ABO incompatible couples to join the kidney exchange program, but even the compatible pairs can join. So the compatible pairs do join the programs in many countries, especially in the UK. So here we did this survey back like 10 years ago, but this is quite the same situation still. So what countries compatible pairs are allowed to join the kidney exchange program? You can see that, for instance, in France, they are not allowed. And in Germany, actually, this is also in the draft legislation, they want to forbid the participation of the compatible pairs, which is, I believe, a stupid decision because the compatible pairs can not only gain by getting a better quality kidney, but they can also help others to facilitate exchanges. And actually, this is very interesting, because if you study the performance of a kidney exchange program, you always have to care about the strategies of the players, strategies of the patient pairs. So if you are a compatible pair or an ABO incompatible pair in France, where the kidney exchange program is working very poorly, what is the chance that you will get an offer in 3 months' time or 6 months' time? Very small. So it is actually a rational choice to go for the direct transplant immediately and not to waste the time. In the UK, however, where there is a lot of compatible pairs, very rich pools, the chance that you will get an offer for a good quality kidney is high. So even if you are a compatible pair, it's a rational choice to join the kidney exchange program for 1 or 2 match runs. So these are different Nash equilibrium cases. You know, in a good performing kidney exchange program like in the UK, it's actually a rational choice for you to join the kidney exchange program, even if you are a compatible pair, because you are quite likely to get a good offer. But if a country is in this bad equilibrium, like France and Italy, even if they allow some countries, they don't even allow the participation of compatible pairs, but even if they allow, it's not a rational choice for the compatible pairs to join, because they just wait and lose time. So they just wait in vain. Okay, so anyway, so back in 2016, we did this survey. You know, what are the legal possibilities? Registering, for instance, multiple donors. This is quite normal in every country. So if you have your wife as a willing donor, you can also register your brother, for instance. And by doing that, you increase your chances that you will be involved in a cycle. Actually, sometimes ABO incompatible transplantation is also possible in the cycles. So this is what they do in Scandia transplant. Typically, the organs are shipped, but there are some countries like in the Netherlands where the donors are traveling. And here you can see what is the upper bound for the number of patient pairs in a cycle or in a chain. So typically, the upper bound is 3 for the cycles. This is 4 for the Netherlands. But there are some countries, actually in Prague, there is a crazy professor, in a good way crazy. He's taking risk. So he performed already 6 and 7 way cycles. When we had a workshop there, he actually performed for us a live donation. So we were sitting in a room and watching a big screen, and he did the operation in the next room. So that was, anyway. So we had many, many interesting stories in this project, but I don't want to waste too much time. Yes? Yes, ABO incompatible transplant. So also in a kidney exchange cycle, this is possible that the donor and the recipients are ABO incompatible. In that case, the recipient has to go through a desensitization treatment before the transplantation. Again, this costs like 100,000 euro. So this is costly and coming with an extra risk. But again, if this recipient is really needing a kidney, and you know, so there are many factors that makes a recipient very desperate, like not just the health status. There is also the so-called PRA value. So PRA value will tell you if your PRA value is 95%, then from 100 random donors, you can only accept 5. So the higher the PRA value, the less likely that you are able to receive a compatible pair. So usually, if the PRA value is very high, like 98, 99, or even more, then they do also consider ABO incompatible transplants in a cycle. Okay, so here are the optimization policies that I promised. So we had this second paper published in EJOR, where we surveyed what are the policies they are using. And typically, these are hierarchical optimization policies. So as the first goal, they maximize the number of transplants, except in the UK, where they have a very special rule for the first objective. And then there are second priorities, third, and so on. So this is hierarchical optimization. And those factors which are highlighted in blue, they are all quality factors. And so the age of the donor matters a lot. And also the so-called age-allele matching. Age-allele matching means that how similar is the age-allele type of the donor to the age-allele type of the recipient. The more similar, the better, because then there is after transplantation, there is less risk that antibodies will be developed. So, you know, the ideal transplantation is between identical twins, where the age-allele types are the very same, because then the kidney is not considered as a foreign organ. But if the age-allele types are similar, then we have a better graft survival time in expectation. So as I said, age matters. So the younger the donor, the better the graft survival time. And also age-allele matching matters a lot. So 6 match means that you have the very same age-allele types for antigen A, B, and DR, at least for split resolutions. Anyway, these are all, you know, there are many medical details behind. This is a classical way to measure the similarity of the age-allele types. And 6 is the best score in that. But for instance, in the UK, they use 4 categories. So the point is that quality does matter. And this motivates our first topic, where the age of the donor and the age-allele matching, you know, they really influence what's the expected graft survival time. So in this graph, I just wanted to illustrate that actually in the UK, the patient or pairs can be selective. They can say that they don't accept a kidney which is a poor quality. Poor quality means that either the donor is old, too old, or the age-allele matching is not so good. And this is very crucial, especially for compatible pairs. So if you want to convince a compatible pair to join the program, you have to give quality guarantees. And this is what they give in the UK. They ensure that the age of the donor and the age-allele matching is at least as good as their willing donor, or even more better. And actually, this can be seen in the picture because this is the PRA value. So practically, these patient or pairs should all sit on this 1 minus PRA line, or close to that. However, we see that, because that's by the definition of the PRA. However, we see that, so PRA, I just told that, sorry. So if your PRA level is 95%, then from 100 random donor, you are only compatible in expectation with 5 donors. So because of your antibodies that you already developed. If you have, so high, 90% of PRA means that the proportion of donors that is acceptable for you, it's around 5–10% in the pool. So this is from the pool. If your PRA level is 30, this means that you should be expected to have around 70% of the donors in the pool to be age-allele compatible. In reality, they accept much less, and exactly because they also screen for quality. Okay? Yeah.
But some of them accept a lot, right?
Yeah. So
They are maybe in the poor condition.
yeah. So for instance, they accept. This is an outlier. Let's say maybe they don't have. Yeah. So they can give thresholds. What is the maximum age of the donor they accept, and what is the minimum level of HLA matching that they accept. Yes, yes, exactly. So everybody can have these conditions, not just the compatible pairs, everybody.
It's not given in the law, it's
Patient by patient, advised by the clinicians, obviously. So, and so this can be actually really heterogeneous. Like, you know, if you are a young patient, you really should care about the quality, because it does matter that the new kidney will work 10 years or 20 years or more. So, because, question?
Excuse me, but like from the perspective of a TTC, just like, isn't this just like saying that because they have condition, it changes the preference order?
So, regarding the TTC, I will come back to that question. Hopefully, I will have time. But indeed, TTC is a potential solution that is not used at all in practice, but we are arguing that the policymakers should consider the TTC based on preferences. So having this selection for age and HLA is actually rejecting, so it's screening. So you don't change your preference list. Your true preference list is coming from the quality of your potential donors. You just restrict some of those donors, so you are rejecting. So it's a kind of manipulation. You can be strategic of rejecting some potential donors. Okay, so how can we describe this problem with graphs? So either we have, you know, donors in a bipartite graph on the upstairs and recipients downstairs, and just an edge representing compatibility, or which is more typical is that we have patient-donor pairs denoted by nodes in a directed graph, and the arcs correspond to possible transplant. And we can have weights, where the weights can represent the quality of the transplant. And if we only focus on pairwise exchanges, then actually the problem boils down to a matching problem on a non-bipartite graph, where an edge represents a pairwise exchange. And now the big question, what kind of solution we are looking for? Do we want to maximize the total expected life gains? In that case, we should choose a maximum weight solution. Or do we want to maximize the number of transplants first? And this is what is happening in most European countries. And finally, TTC and stability is yet another possibility. What about finding stable solutions? What is a stable solution, a core solution? So tomorrow in the class we will learn about NTU games and the core of NTU games. So this means that there is no blocking collision. There are no such patient-donor pairs who could deviate from the proposed solution and get a strictly better solution by forming their own exchange cycles. So in this example, patient-donor pair 1 and 2 could collaborate, and they could form a blocking cycle. They would both get better kidneys. In the UK, actually, maybe one recipient 1 or recipient 2 would not accept some bad quality kidneys, and actually we would end up with this good cycle for them. So in practice, we don't know, because of this quality screening, maybe actually we are closer to the stable solutions, but still, according to the official policy, they are maximizing the number of transplants in most countries. Okay, so what are the complexities of these problems? So if we only have pairwise exchanges, then finding a maximum number of transplants or maximum quality, so maximum total weight solution, these are solvable problems by the Edmonds algorithm, because this is just a non-bipartite graph matching optimization problem. For stability, this is actually equivalent to the so-called stable roommates problem that is in the Gea-Shapley paper. So tomorrow, actually, in the lecture, I will explain that more in details. In this case, unfortunately, we are not guaranteed to have a stable solution, But still we can have some, so at least we can decide it in polynomial time, in linear time actually. And for instance, we can look for a solution where the number of blocking pairs is minimized. What about 2- and 3-way exchanges? So this is unfortunately the most realistic scenario, because in most programs they allow 2 and 3 cycles. Unfortunately, everything is hard. So MP hard. In the UK, we developed the graph-based algorithm that we use to solve those problems that I showed you. But nowadays, typically, it's integer programming that we are using. For stable solutions, it's also MP hard. It's actually a kind of generalization of the so-called 3D matching problem. However, you can also use integer programming here. And finally, yes? Yeah. So luckily, these problems are not so big, so we can solve them with integer programming. So this is what we do. So let me show you actually an example for integer programming. This is the basic so-called cycle formulation, where each cycle, each potential cycle will have a binary variable. And the only thing we have to make sure is that every node in the graph is covered by at most 1 cycle. So every donor is only used once. Every patient is only receiving 1 kidney. And this is the only constraint we should make. And then if we want to maximize the number of transplants, then the coefficient in the objective function is simply the size of the cycle. If we want to maximize the total weight, so the number of years gained by transplantation, then again, we just take the weights of the cycles in the objective function. We can also combine these two, either in a hierarchical approach, like first maximizing for the number of transplant, and then taking this as a new condition for the weight maximizing case. But we can also directly find such a solution by combining these two objective functions if we want. And then we can find a solution that first maximizing the size of the matching and then the quality of the matching. So this is typically what is happening in Europe. Okay, and the surprising thing is that if we don't have upper bounds on the length of the cycles, then everything becomes nice. So we can find a maximum size or maximum weight solution easily, and also we can find always a stable, a core solution. And this is the famous top trading cycle algorithm that will do that. So, unfortunately, this cannot be used for kidney exchange because we don't allow unbounded length cycles. But still, we argue that considering stability can be important. Okay, so, yes. For the maximum number of transplants? Yes. Yeah. I thought that I will give this as an exam question on Friday, but no, anyway, I show you. No, this is, I'm just joking. I know, I'm just joking. The reduction is actually pretty simple. So how to maximize the number of transplants if we have unbounded life cycles? Take this bipartite graph and include also the original patient donor pairs with 0 weight edges. And then find a maximum weight complete matching, complete. And completeness will mean that either somebody is matched with her own donor, and in that case, they are not participating in the exchange, or she is matched with another donor, and in that case, her donor is also matched to another recipient, and they are participating in an exchange. So computing a maximum weight perfect matching in this bipartite graph is equivalent to maximizing the number or the total weight of exchanges with unbounded length cycles. That is called as the cycle packing problem in graph theory. So this is a well-known reduction. If you want to read the details, there is a 2007 paper by Abraham et al., and they describe this reduction already. And this is what we did also when we did the simulations for the UK, and we could impress them that we could also solve this seemingly much harder problem. Okay. So, I don't know how much time I use. I'm afraid much more than... Yeah, maybe 20 minutes. Okay. All right, so the point is that now I finished the first part, the introduction, and now I have still two topics. One is fairness for kidney exchange, essentially using stable solutions. And the third topic, let me also speak at least 10 minutes about the third topic, because I also wanted to show that TU games and Shapley value and these sort of things can be used for kidney exchange. So I will speed up a little bit. So stable solutions. We had several recent papers. First paper, we showed how to compute stable solutions for bundle length cycles using integer programming. And second and third paper, we showed some nice properties, in particular, the respecting improvement property. If we have unbounded cycles and we can use the TTC, then the following property holds. If somebody is bringing a better donor or registers an additional donor, then this cannot hurt the recipient in a TTC solution, because in the result of the TTC algorithm, the kidney that she will receive will be at least as good as before this change in the quality. So if you are considering to register not just your spouse, but also your brother, for the TTC solution, this is always a good idea. But if you just maximize the number of transplants, like as we do in Europe, this can hurt you. You bring a second donor, and as a result, you get a worse quality kidney. So this is what we studied in this second paper, and also in the third paper. Okay, so I will speak a little bit about this second paper. So I won't go into too much details about the model. This is the standard Shapley scarf model with the TTC. The point is that there are three core solution concepts. The standard or weak core, where the blocking coalition needs to improve everyone strictly. So we can imagine that we have also some ties. So some kidneys are similarly good. And in that case, a blocking coalition can be either a strictly blocking coalition, and in that case, so the lack of a strictly blocking coalition means that we are in the core of the game. Or we can also define the strong core, where we also rule out blocking coalitions, where it's enough just to have one member of the coalition to improve strictly, and the other can just get a similar quality kidney. This is the difference between core and strong core is also significant if we have only strict preferences, because having the same kidney can also mean that this agent is not participating in a strictly blocking coalition regarding the core if she's getting the same kidney in a blocking cycle, but she may participate in a blocking coalition regarding the strong core. So this difference between strong core and weak core is actually important even for strict preferences. And finally, there is a so-called competitive equilibrium solution in between the two. This is originally defined with prices. So we have an allocation X with supporting prices. So in the original context, we have houses, and maybe it's better to speak about prices when we have houses than when we have kidneys. So let's say that we have an allocation where this is actually a exchange, so reallocation of the houses. And this is a competitive equilibrium solution. If everybody is getting an affordable house, so the price of the house that she's receiving is at most the price of the house that she's giving away. Essentially, they should be the same price. And if somebody is preferring another house than what she received, then this house must be more expensive than her own house. So essentially, everybody will receive one of the best houses in the market that she can afford. So that's the concept of the competitive equilibrium. In fact, this can be defined equivalently by using this concept of vacuum. And this says that an allocation is a competitive allocation. So this definition is very nice because it has no prices included. The definition of the blocking coalition is the following. In a blocking coalition, there must be at least one player who is strictly improving, and the others, they either have to strictly improve or get the very same house. So what is not possible compared to the strong core is that somebody is getting a different house of the same quality. So actually, if we don't have ties, so if all the preferences are strict, then this definition shows that the competitive equilibrium allocations are equivalent with the strong core allocations. And typically, these are the relations. So I don't have the relations, but you know the competitive allocations are always in between strong and weak core. So how can we find a competitive equilibrium allocation? Actually, with the famous TTC, that here is the description. Is very simple. I'm just wondering whether I can tap on this website. I usually, okay, let's see whether it's working. It's always some excitement to use a website. So, but yeah, in this case, this was a bad decision because it's not showing up. Yeah. Oh no, it's coming. Okay. So you can generate a house exchange problem here, and let's see whether it is running. Yes, it's running. So we find the top choices, and then we change the houses for the top choices. This is called as a top cycle. And after making these exchanges, we are removing the agents who are exchanging the cycles in the first round. Okay, let's do another round, populate preferences. So what is the algorithm of TTC? So in the first round, everybody is just pointing to the top choice, and there will be at least one cycle. This is called as a top trading cycle, and we perform the exchange through this cycle and remove the agents. So we just continue with the rest of the market. So this is a very, very, okay, this was not a good example because the only cycle was an on cycle. Here there is a pairwise exchange. Okay, so this is the TTC algorithm, and I'm glad that it worked. And it can be shown that a solution is competitive equilibrium solution if and only if it is obtained by the TTC. And the proof is very, very simple. You can just define the prices according to the order of performing the TTC cycles. Okay, what else we know? So as I said, for strict preferences, actually competitive allocations are the same as strong core allocations. And in general, if we have ties, then the strong core may be empty. So this is a simple example. No matter which pairwise exchange we choose, the other pairwise exchange will be a blocking, weakly blocking, because the agent in the middle, she doesn't care, but the other agent will improve. So there is no strong core solution. But at least we can always compute a strong core solution if there exists one. Okay, I'm afraid I won't have too much time to go into the details. Yeah.
You say it's the unique mechanism because it's not, there's not only one solution for it.
So if if we have a strict preferences, then according to this definition, then it is unique. Yeah. So this is the root. So probably one of the first paper of Air wrote, published in yeah. So they are the same, and it is the unique solution that actually the TTC is producing. If we have ties, then depending on how we break the ties, we can get different competitive equilibrium allocations, some of which might be strong core solutions, some others which may not. So in this case, only agent 1 has a tie, and depending on how we break the tie, we can have 2 different competitive equilibrium solutions, and actually one of them will be a strong core solution, but the weak core is even larger, and actually the maximum size solution is even larger than anything in the weak core. So, and what is the case in every problem is that, you know, the strong core is the most restrictive, sometimes it's empty. Weak core always exists because with the TTC, we can always obtain a competitive equilibrium solution. And because of that, the weak core is also always non-empty. So this was originally the proof of, you know, the Shapley scarf paper using the famous algorithm of David Gale, the TTC algorithm. Okay, so let me come back to that question in 2 minutes. So first of all, what are the theoretical results that we showed in this MOR paper? For strict preferences, the TTC solution has this respective improvement property. So if somebody is improving her house, bringing a better kidney donor, registering a second donor, cannot hurt this agent. So after this improvement, what she will receive in the TTC will be at least as good as before. And let me show you the proof very, very quickly because it's very simple. So if you improve your house, you know, what does it mean, improving your house? Your house will move up in the preference list of some other agent. If this other agent, J, is not participating in any top cycle until you leave the market in the TTC, then this improvement will not affect your allocation. If you originally you participated in the same top cycle with this agent J, who now likes your house better, then this top cycle will change, but you will still get the very same house. So again, this will not affect your solution. The only time when this can matter for you is when this agent J, who now likes your house more than before, has left the market earlier in the original TTC, and now she points back to you earlier, and you can be involved in a TTC cycle earlier, therefore you can get a better house as a result. So among these 3 basic cases, in the last case, you may get a better house. In the other cases, you get the very same house. So the proof is very, very simple. This is the proof for respecting improvement for strict preferences with the TTC. And we have also additional results for strong core and competitive equilibrium allocation. Actually, that is pretty interesting, but I don't want to spend too much time because, yeah, it would be a bit time-consuming to go through this example. Actually, we studied also this recently, so there are still some open questions for competitive equilibrium. We had this DAC2 seminar last summer, and we considered some complexity questions, but again, I will skip that in order to have enough time for the International Kidney Exchange. And regarding the preferences, it's actually even more complicated. not just having strict preferences and ties, you may even have partial orders, which means that if you only prefer a kidney if the donor is younger and the age-area matching is better, which is the case in the UK, then it may be that we have here actually 3 kidneys. So I am the patient, I'm considering 3 kidneys. The red kidney is better than the blue kidney because the donor is younger and the age-area mismatching is also smaller, so the age-area matching is better also. So that's surely better. But it may be that another kidney is this is better regarding the age, but worse regarding the age-area matching. So it may be the case that we have, so this is called as a partial order, where we have indifferences, and the indifference relation is not transitive. So it's not even ties, because it's maybe that 2 kidneys I'm indifferent, and I'm also indifferent between these 2, but I have a strict preference for those. Yeah, you are right. You're absolutely right. So there are actually some scores, such as the RKDPI index. So this is an index for quality for living donation. And this will give you one particular score where there are many factors taken into account: age of the donor, age-area matching, and even the genders and other stuff. So in that case, you're right, you have strict preferences. But if we consider multiple attributes, and maybe we are not sure how to weight these attributes, then maybe we have actually partial orders. Okay, I finished this. I just wanted to show this example to illustrate that if you bring a better donor, it may hurt you. Because in the largest solution, you may get a worse quality kidney. So before registering the sister, this patient was getting a kidney, a good quality kidney, but after registering her sister, there was another cycle, and using the other cycle, we could get a larger solution. So if the optimization is about maximizing the number of transplants, then this respecting improvement property can be violated. And in this paper, what we did, we considered when it can be violated, how it can be violated, and then we also tested this in simulations. And for testing it with simulations, we used actually integer programming. I won't spend time with that. With the students, actually, I will study some integer programming approach for college admission and other applications. Here, it's also very interesting that you can do in an efficient way. So already Quint and Waco had an integer programming formulation for core, competitive equilibrium, and strong core, but this was highly exponential in the number of constraints. So it was not effective at all. They had one constraint for every possible cycle. And in our description, it's much, much better, much less variable, much less constraints. And actually, it's also nice, I think, because when we move to core, to competitive equilibrium, and then to strong core, we just add some new restrictions. And this also shows that these solution concepts are getting more and more restricting, demanding. Okay, anyway, so this is what we use to conduct simulations, and what we compared, what is the maximum number of transplants we can achieve with a traditional way, maximizing the number of transplant versus finding a core or strong core solutions. And we also tested the how many violations we have for the respecting improvement property. And the main lesson was that if we just maximize the size or the weight, we do have many, many violations. And compared, if we find a stable solution, even with bundle length cycles, then the number of violations is very, very minimal. For the TTC, obviously, we don't have any violations because of the theorem I showed you. For bundle length cycles, we can have some violations in theory, but in practice, we don't see basically any. So if we only consider 2 cycles and 3 cycles, so the theory is when we have unbundled length cycles, then in the TTC, we don't have any violations for the respective improvement. In practice, we have bundled length cycles, 2- and 3-way cycles, and we have examples to show that there can be violations. But in practice, simulations, yeah.
Can you from data, real data, test the
Yeah.
Is it also possible?
Yeah, let me show you some simulation stuff here in the last part. So this is the third part about international programs. We have a simulator that we developed, so we can generate realistic instances, but we can also work with real instances. Actually, in this new project that we are participating in, we are collecting real data sets. So in the coming few months, we will actually get real data sets from all the partners. And we will, historical data sets, so for few years, because this is very, very crucial to do the simulations always for a time interval. So if you change the policy, maybe for one matching rank, you get a better solution in the number of transplants or quality, but you always have to evaluate a policy in the long run, in 5 years. So if you use all the easy to match patient pairs today, then in 3 months' time, your pool will not contain many possible cycles. So that's why there are some prioritizations. So if there is a very hard to match patient pairs, typically we give priority. This can be the PRA value or blood types or other reasons why this patient pair is very hard to match. And then there are prioritizations. And also regarding the blood types, if we have a blood type O recipient, then she can only receive ABO-compatible kidney from a blood type O donor. So if we have a blood type O donor, we should not waste this donor for other patients. So these things matter a lot in the long run, but not for one matching run. So that's why we always do the simulations for the long run. Yeah. No, they pretty much kept the same policy, but they made many, many changes in the whole process. What data do they require, and how the decision is made? Actually, what they introduced, what is very crucial, is a so-called pre-matching phase, where the clinicians can double-check all the potential donors before the match run. So this is very important because if we first do the match run, select the cycles, and after that we ask, okay, is this acceptable for you? Then in many cases they reject because it's not good enough. This is what happened in Hungary, actually. Exactly, this is what happened. We identified a lot of cycles, like 10 cycles probably, for the last 2 years, and they managed to perform only one of them. And in most cases, the reason was that there was at least one transplant which was not good enough in quality, and the doctors rejected it. And you cannot do anything about that. So you have to pre-screen that before the match run. So this was one important invention in the UK program. They have this pre-match run. First of all, they screen regarding the age and the age-LM matching. So this is an automatic screening. But after the automatic screening, the doctors then they still can decide not to accept some donors if these are complex. So anatomy can matter, how many vessels, arteries they have, and so on. And they can still reject some of these potential before the match run and after. Yeah. But as a result, the success ratio in the UK went up dramatically. So after, if you pre-approve these offers, and after then you find the cycles, then it's almost sure that they will accept because they pre-approved already. Exactly. So it is not so there is a constant discussion with all the partners, and as I said, next week you can attend this webinar and you can hear all the details about the UK program. No. This is actually the very first time. This is part of this project because we would like to be transparent, and actually the German decision makers are also invited, so hopefully they will attend that and like. Yeah. So this is open for everyone. Yeah. Okay, so the last topic, I try to be very brief. I don't want to. Yeah, so let me at least to reach the point where I explain why the Shapley value can be used, because I just want to make it sure that the students who just learned the Shapley value today in the course, they see where it can be used. And after that, I will take it slow, and I don't mind if the students or anybody is leaving. So I'm very happy to stay as long as you want, but I try to be quick to reach the Shapley value. And then, everybody is welcome to leave. And I'm very happy to answer all the questions. So I'm here the whole week, so you can ask me. So first of all, international kidney exchange. So this is happening the last 10 years in Europe. First, they started in between Prague and Vienna. They just met at the border, exchanged the kidneys, went back to the capitals, and transplanted. So this was like quite an ad hoc collaboration at the beginning. Now they actually involved also Israel, so this is this became a big collaboration. There is also, as I mentioned, a collaboration among the Scandinavian countries, and this is due mostly to Tommy Andersson. I remember like 7 years ago he announced on Facebook that this international kidney exchange is happening already in Scandinavia. And since then, this is really became a nice example of international programs. In the new project, they are very much active, the Scandinavian transplant colleagues. And as I also mentioned, there is a collaboration in between Italy, Spain, and Portugal, although their collaboration is a bit more conservative in the sense that first, they always conduct the national match runs, and only with the leftover patient donor pairs, with the hard-to-match patient donor pairs, they try to find international cycles. And obviously, you can imagine that this approach is, it's more conservative, and the results are also worse than when they would, join the pools. So I will actually show some simulation results comparing the collaboration policies. So, as I said, we developed the simulator back in the cost action, and we use this simulator to do various policy testing. One is a general paper describing the main aspect of the simulator. In the other paper, these are students. They were MSc students conducting the simulations, supervised by us. And then, so the other paper is about reoptimization. So this is another interesting topic. So this is the basic process of the simulator. So we can either take a historical data set, so patient donor pairs registering to the pools. This is what we will get soon from the partners, or we can just generate data. And the generated data is also quite realistic because we take the parameters of the real pools into account, like what are the PRA distributions, what are the plot type distributions, and so on. So anyway, either we take a real data or generated data, we, just run the simulator. So this is a dynamic simulation. We have typically like a 5 years interval with match runs in every 3 months. And then we just evaluate the solution. So this is a typical simulation where we compare the 3 policies. So there are 3 countries, UK, Netherlands, and Spain. Either they don't collaborate at all, or they fully collaborate, or in between, they just use this conservative collaboration where they first run the national match runs, and only with the leftovers they look for international cycles. So these are with generated data sets, but you can see that, obviously when they join the pools, that's when they can have the most transplants. Okay, and we can also analyze, how much these countries are gaining from the collaboration and so on. Now, here comes the Shapley value part. So, imagine this situation. Spain and Portugal and Italy, they collaborate, as actually in reality. So, suppose that there is a pairwise exchange possible for Portugal. But one of the patient donor pairs in Portugal could be involved in a free cycle with 2 Spanish patient donor pairs. So what to do here? So in Scandinavia, they would just do the free cycle. For Portugal, Italy, and Spain, they would do the national run first, so find this pairwise exchange, and then this free cycle would not appear. What we are proposing is always to maximize the number of transplants, but keep track what are the benefits of the countries. So in this case, if we choose the free cycle, then obviously Portugal will lose. They will only get 1 transplant instead of the 2 that they could achieve alone. So this solution is not even so-called individual rational. They could get more just by doing the transplant within the country. In fact, when we consider this is a cooperative game where the countries are the players, we can then define what are the fair shares. So so what is the total value that they can generate? Total number of transplants. This is free because we can have free transplants in the free cycle. How they should share this revenue? So if we take the Shapley value, or actually the nucleus would give the same, the fair share for Portugal would be 2.5, and the fair share for Spain would be 0.5. Because what is the benefit they are bringing? So class today, if Portugal is coming first, then they can already achieve 2, and then Spain is coming, they can achieve 1. If they arrive in the other order, Spain can achieve nothing, and Portugal arrives, they can achieve 3. So the average marginal utility for Portugal is 2.5, and the average marginal utility is 0.5. So this is how we get the Shapley value. But actually, the nucleus would be the same. Okay, what we do with these fair shares, we have these as target values. We try to find a solution where the number of transplants is close to the target values. Here, there is a unique optimal solution, so we cannot do anything, just perform this 3V exchange. But we will remember these deficits. So if the fair share of Portugal was 2.5, but they only received 1 transplant, then we will bring this credit of 1.5 forward to the next matching run, and the negative credit for Spain. And if we have a situation where we can choose in between multiple optimal solutions, like here, where a pairwise exchange is possible with Portugal or with Spain, with an Italian pair, then we will prioritize Portugal, and in that case, we will balance out the benefits. So actually, in this situation, now the nucleus and the Shapley value will give different target values. So if you compute the Shapley value, this will, in this situation, this is going to be 1/3 for Portugal and 1/3 for Spain. you remember they are symmetric players, so they should have the same Shapley value. So they all only get this marginal value. So symmetric for Portugal and Spain, not symmetric for all. Yeah. So the only arrival order where Portugal has a marginal utility is when Italy arrives first, and then Portugal arrives second, and then the marginal utility for Portugal is, so actually that is 2, and this is happening only once in the 6 potential cases, so that's why the Shapley value is 1/3. Yes? Very good question. So this is up to the decision makers again. What do you consider as a tie? So if you only care about the number of transplants and you don't care about the quality, then we have a tie. If you have more sophisticated solution concepts, obviously the set of optimal solutions will shrink, and sometimes it's just unique, and this concept doesn't make any difference. So this concept is only meaningful if the set of optimal solutions is relatively large. So here we are just focusing on the number of transplants, and in these papers we kept focusing on that. And yeah, it's actually one aspect of international kidney exchange, whether the policymakers want to balance the benefits or not. So this is very much under discussion. There are many ideas how the countries should collaborate in Europe, and they haven't realized yet, I think, that some collaboration policies will give different benefits to different countries. So this is what we will also demonstrate with simulations. And we hope that after they see our simulations, they will realize that actually some collaborations are pretty unfair for some countries. Just an example, the UK is now considering to join the European program, but only with their hard-to-match patient pairs. This is very unfair, I believe. So they can match basically many patient pairs in their national programs, but they only have problems with some hard-to-match patient pairs where the PRA values are very high, hard to match. Now, if they will only delegate the hard-to-match patient pairs to the European platform, this would harm the other countries. So intuitively, you can only have a hard-to-match patient pairs with some easy-to-match patient pairs. So if the UK is deciding to only send hard-to-match, this is going to be unfair. In fact, in the US, what they do, so there are no countries, but there are big transplant centers. Some of them actually performed much more transplantation than any country in Europe. So what they do in the National Kidney Registry Program, which is the largest in the US, is that they give also credits, but based only whether or not the patient or pair that they register is easy to match or hard to match. If it's hard to match, minus 1,000 score. If it's easy to match, plus 1,000 score. So they make sure that all the transplant centers register roughly equal number of easy to match and hard to match patient pairs. The current thinking of the UK, which I can understand as, I mean, this is a safe strategy. If you just register the leftover hard to match patient pairs, this is rational strategy, but this is going to hurt the other countries. So I believe that when we will demonstrate this with simulations, the policymakers will realize that this is not a good approach. So anyway, this is up to discussion. Yeah, so this is up to discussion. If we use such a game theoretical approach, then this will correct. This will correct. Yeah. So anyway, that's the main concept, and we have done, yeah. Yeah, so now we completely forgot about individual preferences. You're right. we just submitted the grant proposal in Hungary. And first, we would like to do simulations for stable solution concept, as I explained, Then, with credit systems, with real instances, and ultimately, just as you said, combining the two. So individual decisions together with country decisions. So yeah, ultimately that's the way to go. But even in this project, we are only expecting this to happen in a few years' time, where first we understand both and we also test both carefully on real data. Then we can combine the two approaches. But you are right, they should be combined. So anyway, I hope you get the idea, and I hope that the students could understand that the Shapley value and the nucleus are actually pretty useful, even in a setting where there are no payments, but these solution concept can be used to define the fair shares. And in this case, the only core solution is actually when Italy gets 2 value, because if any of Portugal or Spain would get any positive payment in a value, the other pair would form a blocking coalition in the TU game. So just to finish to the students, that this is the unique core solution. This is actually called as a matching game because we match the agents. So tomorrow or Thursday, actually, I will speak about the matching game in the class and some generalizations for countries. So anyway, now if some students would like to leave, then please you can leave. So I reached already the point of the Shapley value and the nucleus, and then I have a few more slides about comparing this European approach with the US situation, the US approach. There are also many papers considering strategic questions for a kidney exchange in the US. As I said, the situation is pretty different, and here are the main reasons why they are different. So first of all, in Europe, these are countries who are participating in the collaboration. So by regulation, all the transplant centers will participate and report full pools. While in the US, what happened, at least in the past, is that many hospitals try to keep the easy-to-match patient pairs and perform in-house exchanges rather than registering the easy-to-match patient pairs in the national program. So they needed to give incentive to the hospitals to report also easy-to-match patient pairs to the national programs. In Europe, this is not the case because by regulation, you can demand all the countries or all the transplant centers to register the full pools. Now, there is also a main difference how the matching is performed. In Europe, typically it's every 3 months we have a match run with big pools, while in the US, there are 3 national programs, National Kidney Registry, Alliance for Pair Donation, and UNOS. And they are actually competing for the patient pairs. And there are also regional programs, and the transplant centers actually still perform more than half of the exchanges. So the matching is immediate. Whenever there is a new registration, they look for cycles immediately, and that's why they don't optimize too much. So the nature of the matching process is very different. And that's also the reason why you have to define the credit system differently. So you have to base that at the level of patient pairs. Furthermore, in the US, the pool compositions are pretty much the same across the country, but in Europe there are many differences. As I just mentioned at the beginning of the talk, ABO incompatible transplantation is pretty standard in some countries, but for instance in Hungary this is not paid. So ABO incompatible transplantation, okay, if you go to Vienna, maybe you can get reimbursed, but this is not a standard procedure. And there are many reasons why the pools can be very, very different across countries. So Spain, for instance, the deceased kidney allocation is working so well. Usually they can treat all the patient pairs in the deceased program, except the hard-to-match patient pairs. So that's why their kidney exchange pool is also more filled with the hard-to-match patient pairs than in other countries. And finally, as I said, there were some proposals, and in actually the National Kidney Registry, the largest US application, they use a credit system based on whether or not a pair is hard to match or easy to match. So essentially based on the marginal benefit they are bringing to the market. While in our compensation scheme, we consider game theoretical approaches, where actually some of them is related to, because in the Shapley value, we also use the marginal contributions, but in a different ways than in the US. Okay, and finally, we conducted many simulations. As I said, originally they were published in the AMAS conference papers, later on in EJOR and math programming. I will show you some. Okay, maybe I skip this theoretical part. So there are essentially two computational problems here. First of all, compute what are the fair shares. So for instance, the Shapley value. So computing the Shapley value can be hard, as we have seen also in the class today. And secondly, when we have the target values, we would like to compute a solution, an optimal solution for the kidney exchange, such that the number of transplants is close to the target values. And that's another optimization problem that can be hard. So we solved actually these problems for some cases. And this is what I will talk about in the class more in details. So the corresponding TU game is called as a partition matching game because we have the countries as the players. And then, a coalition is a set of countries. And the value of a coalition is how many transplants this set of countries can achieve. And what we managed to show is that finding a core solution, that's why finding also a nucleus is hard in this case. And we link this problem with the previously studied multiple partners matching problem, where the players had capacities. So this is also a version of the matching game where a player can have multiple partners. So imagine that maybe you are doing, I don't know, tennis games or whatever in pairs, and then maybe you can have multiple partners to play with every week. So there is a very strong connection of this multiple partners matching game with the partitioned matching game. So this is what we analyze in this math programming paper. And so this is in both directions. So actually, we managed to show this MP hardness for the partitioned matching game. And because of this reduction, this holds also for the original capacitated case. Anyway, I won't go into the details, but for the other problems, for finding a solution which is as close as possible to the target, we also had some hardness results and also some solvable cases for pairwise exchanges. And finally, we did a lot of simulations. So this was actually by Marton Benedek in our group. So we compared the solution concepts. So how much deviation in total we will have for the Shapley value, depending on the number of countries. And we compared this with other solution concepts, with the nucleus and other simpler solution concepts. Okay, I skipped. So we studied both cases, which can be solvable in some situation. One is the pairwise exchange, and the other is the unbounded length exchange. So we studied both in these papers. And here is the picture. So there are many hard cases. There are many solvable cases. I won't go into the details. Lastly, let me mention that there are many, many applications where this machinery can be potentially used. Home exchange, time banks, and actually there is a new topic that we started. It's called portfolio compression, so in financial networks, where these are banks or companies owning money each other, and if you find a cycle, then you can eliminate these obligations. So it's called as portfolio compression in the finance literature, and finding these cycles is very, very similar to find cycles for the kidney exchange. The difference here is that there are some volumes also. So what is the amount of money that you can clear? And this is, I think, a very nice topic. There are already some papers and some applications where they claim they compress a huge amount of money. And actually, we had a colleague coming from Romania, and there was a PhD student doing simulations for a Romanian case. And they used actually this software in the ministry. So they wanted to reduce the debts in between the companies. And in fact, there was another similarity here because they wanted to limit the length of the cycles, because if they suggested a cycle for companies, all the companies in the cycle had to agree in order to have these debts eliminated. So the smaller the cycle, the more likely that they eventually agree. So that's why they also limited the length of the cycles. So anyway, this is another nice application. If you are interested, I'm happy to chat about that. We started some theoretical and practical work also on that. The machinery is very similar to the kidney exchange problem. And finally, this is probably these are the last slides, yes. So as I said, we had a cost action first, then actually a Capsoft Innovators Grant that was about to develop a software, which is called Capsoft. And now this software is actually used in some countries, in particular in Spain and in Hungary. And we are now further developing this software in this new project, which started 2024 November actually, for 3 years. So we will have the next meeting in Madrid in May. And we are still developing this platform. For instance, screening for the quality. This is now what we are implementing. And we make this available for all the European partners. But, you know, there is a challenge. You know, we cannot just rely on European projects or research funding. So actually, in this Capsoft grant, they expected some business plan, how you can make this sustainable. And in the end, the solution was that we funded a non-profit company. It's called Capsoft Collaborative. And this company is doing the utilization of the software. So, you know, it's not anymore up to the universities or research groups to utilize and further develop the software. Obviously, we are still doing most of the work, but now there is this not-for-profit company taking responsibility for the licenses and so on. So this is also very interesting from that perspective, that if you try to contribute as, you know, as a professor, as an you know, from academia to real-life projects, sometimes there is this issue, how you can make these applications, you know, long-term operating. And this is, I think, a very nice solution to have a non-profit company to run the software in the long term. Not for profit. Not. So. Yeah. So the main concept is that we are so this company is collecting membership fees from the partners, from the blood and transplant organizations who would like to use this software. They contribute like 10,000 or 15,000 euro per year as a membership fee. And from this revenue, we can have at least one programmer and some staff to do the administration. Yeah. It's auto-financed, but No. So at the moment, it's only for the. So there is one software engineer. So at the moment, we have Will, who is the lead developer. He used to be a postdoc in David's group. Now he's officially employed by this company. And there are some others, like, there is a CTO and, some but basically they more or less doing this at the moment for charity. In the long run, obviously this should be taken more seriously. So the software developer is the key, because we have to maintain and further develop the software and also do the support. So if some country is running the match run with the software and there is any issue, any support needed, then we need some software developer. In this European project now, we are getting funding actually also in Budapest. So we have 2 software developers working on Capsoft until the end of June. So for 18 months we received money for programmers. But after June we will have no programmers. So actually we try to develop as much feature. So like this quality screening feature, we would like definitely to finish developing by the end of June. But there are always some new ideas, using machine learning for calculating the expected graph survival times, so there are many new ideas always. So it's a continuous challenge to keep the software up to date. And I haven't even mentioned, HLA technology. So HLA typing traditionally is at low resolution, but now they do it at high resolution, so it's much more precise. But then there are many questions. How do you convert the data if some countries is using low resolution, other high resolution? So there are many technical details. So in this project, imagine I was responsible for this software development. We actually had to start a working group on HLA. So this was an HLA working group with HLA experts, and we had to understand all these processes, virtual compatibility testing, HLA matching, so quality screening, PRA calculations. There are many details that matter a lot. So anyway, now I also learned a lot, but still it's an ongoing challenge. So in the US, they use new technology, like applet matching. I believe this is something we should also implement in Europe, but we have to understand the details and yeah.
Our objective now is to make it happen also in Africa.
Yeah. So I think, this is, I'm always, I'm always very enthusiastic. So my personal motivation is, always coming, how we can make the world better for, getting more transplants, school choice, making families, students happier, college admission, and so on. So there are many applications. So for me, that's always the main motivation for doing research. But sometimes it's indeed very challenging to interact with decision makers, understand what are the features.
But who are when you want to discuss with decision makers in the UK, who are ministers?
No, so they have the headquarters in Bristol, and Lisa Burnaff, she's actually usually the one who is representing. But we have also an IT expert, Matthew Robb. So
At the moment, it should be the legislature should decide and vote a law.
So usually there are governmental agencies. So for instance, in Hungary, we also have a blood and transplant organization. There is a transplant director, and there are some scientific committees. So if they decide to change the optimization policy, the regulation for the match runs, they discuss it with the... Yeah.
Someone out of your family. I'm surprised because you said that usually your spouse cannot donate to you because you have a child.
Yeah. In Hungary, the first exchange happened this January, a few weeks ago, and actually 2 pairs were involved, 2 married couples, and the women were the recipients, so they received kidneys. They could not receive from their husbands, and they received through the exchange. So that was a success story. So I mean, in Germany, you know, they are still debating on this law.
What is the main reason, for example, Germany is debating, given the numbers you give, the success in the UK, the US?
Yeah, it's a very good question. So they are always a bit too worried about not to put pressure on the potential donors. So if there is a direct transplant possibility, yeah. But if the donor is not compatible with the wife, they don't want to put any pressure by having the kidney exchange program. So there would be like a social pressure. Why don't you register to the kidney exchange program? You could save your wife. If there is no kidney exchange program, there is no pressure. I think that's the, but there are other reasons. There were some scandals.
Also some, for example, when you don't have, then people that have dialysis. What is
Dialysis, yeah.
dialysis? So there are a lot of people making a lot of money because they have clients for life. Once you save
Sure,
them, then
sure.
you don't need to do dialysis.
Yeah, so these are huge industries, sure.
So I guess there are a lot of actors that
Yeah.
would not want this kind of program to happen.
Yeah.
How do you avoid this kind of thing?
I mean, in the end, it's the interest of the state, of the government, to save money. In the US, actually, the healthcare system only uniquely used. So the unique organ where everybody has an insurance in the US is the kidney. So if you have a kidney failure, you get the dialysis for free in the US. This is the only organ for which you get this treatment. And that's why actually the share of the kidney treatment, the dialysis cost, in the US healthcare, state healthcare budget is way much more than for any other diseases. So I'm just saying that there are huge monies involved also. As I mentioned, one ABO incompatible transplant costs like 100,000 euro. You can save a lot if you want. But so having the kidney exchange program, I believe this is really giving a lot of benefit to the people. So they are not just, so compared to dialysis, they not just survive, but they can actually work. They can have a normal life. With dialysis, you cannot do that.
Some industrial, they will lose money.
Yeah, sure. But in the end, if you think about the point of view of a government, of a state, having a kidney exchange program is definitely a...
For it to happen, it should be the state.
Yeah. I believe that, you know, the state has a clear incentive because there are so much financial benefit. You can save a lot from not having dialysis. So 1 year of dialysis also costs like 100,000 euro or the same amount of dollars per year. So there are many benefits, and these patients are coming back to, you know, work, and they can have a good life. So this is really, I think, having a kidney exchange program is really beneficial for the countries. So.
Let Peter go. He was teaching 4 hours.
That's right.
The cameraman would like to go.
Yeah. So, okay, thank you. No, thank you for staying so long, and yeah, see you tomorrow in the class.